Welcome to Sleepy Systems. Tonight, we're exploring how the largest container ships on Earth are built. From giant engines to storms powerful enough to bend steel in the middle of the ocean. Before we begin, leave a comment telling me where you're watching from, and let me know what you think. Will container ships keep getting bigger, or are we finally reaching the limit? If you enjoy videos like this, don't forget to like and subscribe. Thanks for being here tonight. At first glance, a container ship does not feel mysterious. It is easy to look at one from a distance and see nothing more than a giant floating rectangle carrying thousands of colorful metal boxes across the ocean. But the deeper you look, the stranger these ships begin to feel. Nearly every object inside an American home may have spent time on one of them. Phones, shoes, televisions, coffee makers, furniture, batteries, toys, even parts of the buildings people work inside every day. Entire sections of modern life quietly move across the oceans inside steel containers, stacked higher than apartment buildings, crossing storms in darkness while most of the world sleeps. And yet, for most of human history, nothing like this existed. Ports were once chaotic places, filled with ropes, wooden crates, shouting dock workers, and mountains of cargo that had to be loaded piece by hand. Before container ships transformed global trade, loading a single cargo vessel could take days or even weeks. Workers carried sacks of coffee, barrels of oil, bundles of cotton, crates of machinery, and boxes of food individually into the belly of ships. Every company used different packaging sizes. Every port had different systems. Cargo was constantly damaged, stolen, delayed, or lost. Historians sometimes describe old ports as bottlenecks of the industrial world, because even as factories became faster and railroads spread across continents, moving goods between countries remained painfully inefficient. In many ways, the oceans themselves were not the slowest part of global trade. The ports were. Some researchers argue that this hidden inefficiency quietly limited economic growth for decades because shipping costs stayed unpredictably high. A factory could produce products quickly, but getting them safely across the world was another story entirely. Then, in the middle of the 20th century, an idea appeared that sounded almost too simple to change the world. Instead of loading thousands of separate objects onto ships one at a time, why not place everything into large, standardized metal boxes that could move seamlessly between trucks, trains, and ships without ever being unpacked? Today, the concept feels obvious, but at the time, it disrupted nearly every part of global transportation. The man most often connected to this revolution was an American trucking entrepreneur named Malcolm McLean. In the 1950s, McLean became frustrated watching trucks sit for hours at crowded ports, while workers slowly unloaded cargo piece by piece. According to several accounts, he began imagining an entirely different system where the truck trailer itself could simply be lifted directly onto a ship. That early idea eventually evolved into the modern shipping container. What made the concept so powerful was not just the metal box itself, but standardization. Once containers followed the same approximate sizes worldwide, entire industries could reorganize around them. Cranes could be designed specifically to lift them. Ships could be built specifically to carry them. Rail systems, highways, warehouses, and ports could all connect into one giant synchronized network. Some economists later argued that containerization may have contributed more to globalization than the internet did in its early decades, because it dramatically lowered the cost of moving physical goods around the planet. And once shipping became cheaper, something unexpected happened. Companies no longer needed factories close to customers. Manufacturing began spreading across oceans. Supply chains stretched across continents. Products designed in California could be assembled in China using materials from Australia, copper from Chile, oil from the Middle East, and electronic components from South Korea before being shipped back across the Pacific to American stores. Slowly, the world economy started behaving less like separate national systems and more like one interconnected machine. But as trade expanded, the ships themselves began changing in size at a pace that almost felt unnatural. Early container ships carried only a few hundred containers, then a few thousand, then 10,000, then 20,000 or more. Each generation seemed impossible until the next one appeared. And the logic behind this growth was brutally simple. Bigger ships could transport more cargo while using proportionally less fuel per container. Shipping companies realized that one enormous vessel crossing the Pacific could potentially move goods more efficiently than several smaller ships combined. In theory, the larger the vessel became, the cheaper global trade could become. But oceans do not care about economic theory. As ships grew longer and heavier, engineers began running into problems that sounded more like physics experiments than transportation challenges. A fully loaded mega container ship can stretch close to a quarter-mile long and carry cargo weighing hundreds of thousands of tons. At sea, these vessels do not sit still on calm water. They twist, bend, flex, and vibrate continuously under the pressure of waves. In rough storms, parts of the hull may experience forces so extreme that the ship subtly bends along its entire length. Engineers even have specific terms for these movements. Hogging happens when the middle of the ship bends upward. Sagging happens when it bends downward. The larger the vessel becomes, the more dangerous these stresses can become. Some naval architects have compared designing megaships to building a skyscraper that must survive earthquakes non-stop for decades while floating on moving water. And unlike buildings, ships cannot rely on solid foundations beneath them. They survive entirely because physics allows displacement to counter gravity. That balance becomes increasingly delicate as dimensions grow larger. There are also limits imposed by the world itself. Some ports are not deep enough for giant vessels. Some bridges are too low. Some channels are too narrow. For decades, canals like Panama and Suez effectively controlled how large many ships could become. Entire classes of vessels were designed specifically around the maximum dimensions these waterways allowed. Terms like Panamax eventually became part of shipping language, referring to ships built precisely to fit through the Panama Canal before its expansion. But global trade pressures kept pushing against those limits. Companies wanted bigger ships because competition in global shipping became fierce. A tiny improvement in efficiency could mean millions of dollars saved annually. And so ports deepened harbors. Cranes became taller. Canals expanded. Entire coastlines were reshaped to accommodate vessels that previous generations would have considered absurdly oversized. Yet, there has always been quiet debate about whether this endless growth truly makes the system safer or more fragile. On paper, megaships are extraordinarily efficient, but some analysts believe they may also concentrate too much global trade into too few vessels. When one giant ship encounters problems, the consequences can ripple across continents. Modern supply chains often operate with astonishingly little margin for disruption. Stores may only hold limited inventory because companies depend on constant deliveries arriving exactly on time. That system works remarkably well until something interrupts it. A storm, a port shutdown, a labor strike, or sometimes a single ship stuck in the wrong place at the wrong time. What makes container ships fascinating is that they are not merely vehicles. They are physical expressions of how modern civilization functions. Their growth mirrors humanity's growing dependence on invisible global networks. In many ways, the average person rarely thinks about the oceans anymore. Satellites, airplanes, and the internet dominate modern imagination. But around 90% of world trade by volume still moves by sea. The oceans remain the hidden highways of civilization. And container ships are among the largest moving structures humans have ever created to travel across them. There is also something psychologically strange about their scale. From nearby, megaships almost distort human perception. Their hulls rise like steel cliffs above the waterline. Their engines are taller than houses. Their propellers can weigh as much as tanks. Yet despite their enormous mass, they move with an eerie quietness through open water. At night, some appear on the horizon like floating cities covered in lights. Sailors sometimes describe seeing them emerge from fog with an almost unreal presence, as if entire industrial districts had somehow drifted out into the ocean. And perhaps that feeling captures why these ships continue to fascinate people beyond economics alone. They represent a strange collision between engineering precision and the uncontrollable power of nature. Humans built them to dominate distance, to shrink the world, to make oceans feel smaller than ever before. Yet the deeper engineers pushed these designs, the more they discovered that the sea always imposes its own rules eventually. Every increase in size created new mysteries about stability, structural stress, fuel efficiency, weather behavior, and even the future of global trade itself. Some experts believe container ships may continue growing larger in coming decades. Others suspect the industry may already be approaching practical limits, where additional size no longer creates meaningful advantages. There is no complete consensus. What is certain is that these vessels did not appear suddenly. They emerged from decades of experimentation, competition, risk, and increasingly ambitious engineering. And behind every one of them lies a construction process so massive and complex that it can feel less like building a ship and more like assembling a floating industrial world from the ground up. Long before the first sheet of steel is cut, before the engines arrive, before cranes begin lifting structures heavier than airplanes, the largest container ships in the world already exist in another form entirely. They begin as calculations, simulations, arguments between engineers, and thousands of invisible decisions hidden inside computer models that most people will never see. Somewhere inside a quiet design office, far away from the noise of shipyards and oceans, naval architects sit in front of glowing screens, trying to solve a problem that sounds almost impossible when stated plainly. How do you create a moving structure longer than many skyscrapers are tall, heavy enough to carry entire sections of global trade, while still making it efficient enough to survive brutal economic competition, and strong enough to endure years of storms at sea? The deeper engineers pushed container ships into extreme sizes, the more ship design stopped resembling traditional shipbuilding and started looking more like advanced systems engineering. Every part of the vessel became connected to everything else. A small change to hull shape might slightly improve fuel efficiency, but also alter stability during storms. A wider ship could carry more containers, but suddenly, certain ports might no longer accommodate it. A larger engine could increase power, but consume more fuel and generate new vibration problems throughout the structure. There is no perfect design, only compromises carefully balanced against each other. And perhaps that is what makes these ships fascinating. They are not masterpieces in the artistic sense. They are moving negotiations between physics, economics, weather, politics, and human ambition. Modern container ship design begins digitally. Engineers now create highly detailed 3D models where almost every pipe, cable, fuel tank, and structural beam can be simulated long before construction starts. Some of these models become so complex that they resemble virtual cities more than vehicles. Entire teams specialize in different sections of the ship. One group studies hydrodynamics, another focuses on structural stress. Others work on propulsion systems, electrical systems, cargo layout, fire suppression, navigation, or fuel efficiency. Even airflow across the stacked containers can matter, because wind resistance becomes increasingly significant at massive scales. Early in the design process, engineers usually focus on the hull, because the hull quietly determines almost everything else. To an untrained eye, modern container ships may appear simple compared to cruise ships or military vessels. Many look like giant steel rectangles floating on water. But beneath that simplicity lies years of refinement. The shape of the bow alone can dramatically influence fuel consumption across thousands of miles. Older ships often had more vertical bows, while many newer megaships use bulbous bows, rounded protrusions extending beneath the waterline. At first glance, they look strange, almost unnatural. Yet their purpose comes directly from wave physics. As a ship moves, it creates its own wave patterns. A properly designed bulbous bow can reduce wave resistance by interfering with those patterns in ways that slightly decrease drag. The improvement may sound small, sometimes only a few percentage points, but across decades of operation and millions of miles traveled, even tiny efficiency gains can save shipping companies enormous amounts of fuel. In global shipping, small improvements become gigantic when multiplied over time. That pursuit of efficiency pushed ship designers into increasingly advanced simulations. Engineers now use computational fluid dynamics, often called CFD, to study how water flows around the hull in virtual environments. These simulations allow designers to observe turbulence, pressure zones, and resistance patterns before anything physical exists. Some researchers compare it to creating artificial oceans inside computers. But simulations are not always enough. Despite modern technology, many shipbuilders still rely on physical testing using scale models placed inside long experimental water tanks. In these facilities, miniature ships move through controlled waves, while sensors measure stability, drag, and behavior under different conditions. Watching these experiments can feel oddly surreal. Tiny ships glide through artificial storms, while engineers stare silently at monitors, searching for invisible weaknesses that might one day become catastrophic on the real vessel. There is something deeply human about this process. Even with advanced computing, engineers still seem reluctant to trust mathematics completely when oceans are involved. Perhaps history explains why. The sea has a long record of humiliating overconfidence. Throughout maritime history, ships once considered revolutionary or unsinkable often revealed flaws only after entering real conditions. And mega container ships introduced entirely new concerns that earlier generations never faced. One major problem is structural flexing. A ship 400 meters long does not behave like a rigid object. In heavy seas, different sections may rise and fall on separate waves simultaneously. The vessel twists subtly across its length. Metal expands and contracts. Tiny stresses repeat millions of times over years. Engineers sometimes describe fatigue as one of the most dangerous invisible enemies in ship design, because failures often emerge gradually rather than dramatically. A structure may appear perfectly fine until microscopic cracks slowly spread through steel over time. To predict these stresses, designers build extensive structural models that simulate how forces move throughout the hull during storms, cargo loading, and long voyages. Certain areas become critical zones where reinforcement is necessary. Some sections experience concentrated stress near cargo holds because modern container ships essentially contain massive open spaces cut into the hull to store containers. Those openings create structural challenges somewhat similar to cutting giant holes into a bridge while still expecting it to remain strong. The larger ships became, the more engineers had to think carefully about how forces traveled through the entire structure. At the same time, economics continued shaping every decision. Cargo capacity matters enormously because shipping companies survive on razor-thin margins. Adding space for even a few hundred extra containers can significantly influence profitability. But increasing capacity also increases weight. More weight changes draft depth, meaning the ship sits deeper in the water. Suddenly, certain harbors may no longer be accessible. Some ports spend billions dredging channels deeper, partly because container ships have grown so dramatically. In some ways, megaships do not merely adapt to the world adapts to them. Entire coastlines, cranes, ports, and shipping routes evolve around their dimensions. And yet, there remains ongoing debate inside the industry about whether ships should continue growing larger indefinitely. Some analysts believe the economic advantages eventually diminish beyond certain sizes. Others argue future designs may become even larger if infrastructure keeps expanding alongside them. There is no universal agreement. One reason is that shipping efficiency depends on countless unpredictable factors: fuel prices, trade patterns, labor costs, environmental regulations, geopolitical tensions, and even climate conditions affecting ocean routes. Designing a megaship, therefore, becomes partly an attempt to predict the future years before the vessel ever enters service. Engineers are not only building for current conditions, they are gambling on what global trade might look like decades ahead. Fuel systems reveal another layer of uncertainty. For most of modern shipping history, massive diesel engines dominated because they provided extraordinary reliability and power. But environmental concerns have begun forcing the industry into uncomfortable transition. Regulations on sulfur emissions and carbon output continue tightening worldwide. Some newer vessels now explore liquefied natural gas, methanol, hybrid systems, or experimental alternative fuels. Yet none offer perfect solutions. Cleaner fuels may reduce emissions, but introduce storage complications, infrastructure challenges, or higher costs. Some experts suspect the future may involve multiple fuel technologies, rather than one universal replacement. Others wonder whether entirely new propulsion concepts could eventually emerge as climate pressures intensify. For now, ship designers often face a difficult balancing act between environmental responsibility and economic reality. Quietly, another challenge also shapes modern ship design: automation. Container ships increasingly rely on advanced navigation systems, sensor networks, automated engine monitoring, and AI-assisted logistics. Some experts believe partial autonomy may become common in coming decades. Others remain skeptical, especially given the unpredictable nature of oceans and international maritime law. But regardless of how far automation progresses, ships are already becoming less dependent on large crews than they once were. Modern vessels carrying billions of dollars worth of cargo sometimes operate with surprisingly small numbers of people on board. This changes the design philosophy itself. Space, once dedicated to larger crews, can now be repurposed for cargo or equipment. Technology compresses human presence while expanding industrial scale. Somewhere during this process, container ships began feeling less like traditional ships and more like floating infrastructure. And despite all the software, simulations, and engineering precision involved, uncertainty never fully disappears. Designers can predict many things remarkably well, but oceans remain environments filled with variables difficult to reproduce perfectly in models. Rogue waves, shifting cargo loads, unexpected weather behavior, and long-term material fatigue still carry unknowns. That uncertainty lingers quietly beneath every blueprint. It may even explain why ship design meetings reportedly involve intense debates, despite the mountains of data available. Numbers help guide decisions, but judgment still matters. Experience still matters. Intuition still matters. Sometimes veteran engineers disagree strongly over details that computers alone cannot settle confidently. In a strange way, designing the world's largest container ships still contains traces of ancient seafaring uncertainty beneath all the modern technology. And perhaps that tension is part of why these vessels continue to fascinate people. They represent humanity trying to impose mathematical order onto one of Earth's most unpredictable environments. Every line on the blueprint exists because someone believed the structure could survive forces most people will never witness directly. Eventually, after years of revisions, calculations, testing, approvals, and negotiations, the digital ship finally becomes ready to leave the screen behind. But at that moment, another challenge begins, because designing a vessel this large is only the first impossible step. The next one may be even harder. Turning millions of digital measurements into real steel, weighing hundreds of thousands of tons, with almost no room for error. And if you've been enjoying this journey into the hidden world behind modern engineering, don't forget to subscribe, because the deeper these ships move into reality, the more unbelievable the process becomes. The first thing that surprises most people about a modern shipyard is not the ships. It is the scale of everything surrounding them. Before a container ship even begins to take shape, the environment itself already feels oversized, as if the entire place was built for machines larger than normal human imagination can comfortably process. The dry docks stretch so far that workers moving across them sometimes resemble tiny figures crossing airport runways. Cranes rise into the sky taller than many downtown buildings. Massive steel sections sit waiting in silence, like fragments of unfinished skyscrapers scattered across the coastline. At certain shipyards in South Korea or China, the operation becomes so enormous that it stops feeling like a factory and starts feeling like an industrial city built entirely around the idea of moving steel. Thousands of workers may be active at once. Trucks constantly carry materials between workshops. Sparks from welding torches flicker across the darkness before sunrise. Giant loudspeakers echo instructions over the wind coming off the ocean. And somewhere inside all this movement, one of the largest moving structures on Earth is slowly being assembled, piece by piece. Historically, shipbuilding was far slower and more manual. Older shipyards often built vessels gradually, from the keel upward, almost like constructing a wooden cathedral over months or years. But modern mega-container ships changed the process completely because they became too large and too economically important to build slowly. Today, many shipyards operate more like highly synchronized manufacturing systems than traditional construction sites. The ship is no longer created in one continuous structure from beginning to end. Instead, it is divided into gigantic sections called modules or blocks. Entire portions of the vessel are constructed separately, sometimes indoors, before eventually being transported and welded together inside the dry dock. This approach transformed shipbuilding efficiency because multiple teams can work simultaneously on different sections instead of waiting for previous stages to finish. In some cases, the blocks themselves already contain installed pipes, wiring, stairways, machinery, and interior structures before they are even joined together. Watching this process unfold can feel strangely disorienting. A fully formed section of ship, weighing hundreds or even thousands of tons, may suddenly appear suspended in the air beneath a colossal crane, slowly drifting across the yard with an eerie smoothness. Some cranes move so carefully and precisely that gigantic steel structures seem almost weightless, despite weighing more than entire office buildings. These machines are often called Goliath cranes for obvious reasons. Certain models rank among the largest cranes ever built, capable of lifting thousands of tons in a single motion. Their sheer scale reflects a deeper truth about modern shipbuilding. At some point, humans stopped building ships with tools alone and began relying on enormous mechanical ecosystems capable of manipulating industrial-scale mass with astonishing precision. Yet, despite the overwhelming machinery, the process still depends heavily on human coordination. A mega container ship may contain millions of individual parts. Every pipe, weld seam, electrical connection, ventilation shaft, and structural support must align correctly. Even small mistakes can become expensive disasters later. Engineers, therefore, organize the construction process through incredibly detailed digital planning systems. Every block receives identification numbers. Every component follows tracked schedules. Workers often rely on digital models that map exact locations for installation down to remarkably small tolerances. In many shipyards, laser measurement systems continuously verify alignment during assembly because slight deviations can create structural problems once the vessel enters the ocean. The strange thing is that container ships often look simple from the outside compared to cruise ships or warships, but internally, they are extraordinarily dense systems. Hidden behind the plain steel hull are endless networks of fuel lines, ballast systems, cooling systems, electrical circuits, pumps, fire suppression equipment, ventilation systems, communication systems, and structural reinforcements. Some sections resemble industrial labyrinths more than transportation vehicles. Walking inside partially completed ships can reportedly feel surreal, with endless corridors of unfinished steel stretching through dim light, while echoes bounce across hollow compartments. Workers sometimes describe the experience as standing inside a giant machine that is not fully awakened yet. The steel itself also matters more than most people realize. Modern shipbuilders do not simply use generic construction steel. Container ships require specialized materials designed to survive corrosive saltwater environments, constant stress cycles, and enormous structural loads over decades of operation. Certain sections demand higher tensile strength because the hull experiences tremendous bending forces at sea. Other areas prioritize toughness to resist cracking under cold temperatures or repeated stress. Ship steel must balance strength, flexibility, weight, weldability, and durability simultaneously. That balance becomes increasingly difficult as ships grow larger. Some researchers have quietly raised concerns that future megaships could eventually approach structural limits where traditional materials become less practical, although opinions differ across the industry. What is clear is that even now, material science plays a major role in determining how far ship size can realistically expand. Once steel arrives at the shipyard, another remarkable transformation begins. Gigantic flat plates are cut using automated plasma or laser systems, guided directly by digital design files. Robotic cutting systems carve precise shapes, with sparks exploding into the air like controlled lightning storms. The noise inside these fabrication halls can feel almost overwhelming. Metal grinding, cranes moving overhead, steel slamming into position, welding arcs flashing constantly in the darkness. Yet, beneath the apparent chaos, everything follows careful sequencing. Timing matters because delays in one section can disrupt entire production schedules involving thousands of workers and suppliers. Some shipyards operate so efficiently that new blocks arrive at the dry dock almost exactly when needed, minimizing wasted time and space. In many ways, the logistics behind building the ship begin resembling the logistics systems the finished ship itself will eventually support across global trade routes. Welding represents one of the most critical parts of the entire process. A mega container ship may contain hundreds of miles of welded seams. Historically, welding flaws contributed to serious maritime disasters, especially during periods when ship production expanded rapidly, without fully understanding long-term material fatigue. Modern shipyards therefore use advanced inspection techniques, including ultrasonic testing and X-ray analysis, to detect hidden defects inside welds. Some welding is performed manually by highly trained workers, especially in difficult areas requiring flexibility and judgment. Other sections rely heavily on automated robotic welding systems designed for consistency and speed. But even advanced automation does not eliminate risk entirely. Tiny imperfections can still matter after years of stress at sea. The ocean repeatedly tests every weld with millions of loading cycles over the ship's lifespan. Somewhere out there in the darkness of the Pacific or Atlantic, every structural shortcut eventually faces consequences. Perhaps that is why experienced shipbuilders often speak about quality control with almost obsessive seriousness. There is also something psychologically fascinating about how modern shipyards compress time. A century ago, constructing giant vessels could take many years. Today, some of the world's largest container ships move from raw steel to launch surprisingly quickly considering their size. Industrial coordination, modular assembly, and digital planning accelerated shipbuilding into something closer to high-speed industrial orchestration. But faster production introduces its own pressures. Shipping companies often demand tight schedules because delayed vessels mean delayed profits. Global trade systems move continuously, and every major ship represents massive financial investment. Shipyards compete fiercely for contracts, especially in regions dominating commercial shipbuilding. South Korean companies became famous for extreme efficiency and technological sophistication, while Chinese shipyards expanded aggressively through scale and state-backed industrial growth. Japan also maintained strong shipbuilding expertise through decades of engineering refinement. The competition between these nations quietly shaped much of the modern shipping industry. And beneath that competition lies another layer rarely discussed openly: geopolitical influence. Building the world's largest commercial ships is not only about transportation. It reflects industrial capability, technological infrastructure, access to steel production, labor systems, energy resources, and strategic economic power. Shipyards therefore become more than factories. They become symbols of national industrial strength. Yet, for all the engineering and economics involved, there remains something strangely cinematic about the moment individual blocks finally begin forming the recognizable shape of a ship. At first, the dry dock appears scattered with disconnected structures. Then, gradually, sections align. The curved bow emerges. Cargo holds take shape. Internal decks stretch farther and farther into the distance. Slowly, the vessel stops feeling theoretical. Workers who spent months fabricating isolated sections can suddenly stand back and realize they are inside something enormous enough to cross entire oceans, carrying the material pulse of modern civilization. And despite all the planning, surprises still happen constantly during construction. Some components arrive late. Certain sections require redesigns. Weather disrupts schedules. Measurements occasionally reveal slight misalignments that demand corrections before assembly continues. Shipbuilding remains too physically complex to become perfectly predictable. In that sense, every megaship is still partly an improvisation, guided by expertise rather than a flawless industrial routine. Maybe that unpredictability explains why these shipyards never feel completely mechanical, despite the automation surrounding them. Human judgment still flows through every stage. Workers adapt. Engineers solve problems in real time. Welders make decisions invisible to future passengers or cargo owners. Thousands of small actions quietly determine whether the final vessel will survive decades of storms safely or develop hidden weaknesses no simulation fully predicted. And eventually, after enough steel sections merge together under the cranes, after enough sparks fade into the night air, after enough workers move across the hull like tiny figures inside a metallic canyon, the impossible structure finally stands complete inside the dry dock. But strangely, even then, the ship still feels unfinished, because the massive steel body is only the skeleton. The part that truly gives the vessel life has not fully arrived yet. Deep inside the ship, engineers are preparing to install something even more extraordinary. An engine so enormous that its scale alone changes how people think about machines. Once the giant sections of the ship finally stand together inside the dry dock, something strange begins to happen. What previously looked like scattered industrial parts slowly starts resembling the outline of a living structure. The curved walls of the hull rise higher each week. Endless corridors appear inside the steel. Cargo holds stretch downward like vertical caverns. Staircases lead into unfinished chambers, illuminated only by temporary construction lights swinging slightly in the wind. And somewhere inside this growing maze, the real challenge quietly reveals itself. Building a mega container ship is not only about making something large, it is about making something enormous behave as though it were flexible, balanced, and alive. while enduring forces powerful enough to destroy ordinary structures repeatedly over decades. The deeper engineers pushed container ship sizes into extreme territory, the more they realized they were no longer simply designing vessels. They were designing gigantic floating skeletons capable of surviving constant mechanical punishment from the ocean itself. Modern container ships are often compared to cities because of their size, but structurally, they may have more in common with bridges. A bridge must distribute force carefully across long distances without collapsing under stress. A megaship faces similar problems, except the foundation beneath it never stops moving. Every wave changes how weight travels through the hull. Every storm twists the structure slightly differently. Every container added to the deck alters stress patterns somewhere else inside the ship. This is why the internal framework matters so much. Hidden beneath the outer steel skin lies an intricate network of longitudinal beams, transverse frames, support structures, bulkheads, and reinforced sections that together form the true skeleton of the vessel. Without this internal structure, the hull would simply deform under its own weight. One of the most fascinating things about these ships is how empty they actually are inside. From the outside, they appear dense and solid, but internally, huge sections consist of vast hollow spaces designed to maximize cargo capacity while minimizing unnecessary weight. Engineers constantly fight a difficult balance between strength and mass. Stronger structures usually require more steel. More steel increases weight. Increased weight reduces efficiency and changes buoyancy characteristics. This creates a quiet engineering paradox at the center of every container ship. The vessel must be strong enough to survive the ocean while remaining light enough to make economic sense. And as ships became larger, that balance became increasingly difficult to maintain. The cargo holds themselves introduce major structural complications. Older ships transporting mixed cargo often distributed weight more naturally throughout the hull. Modern container ships instead contain massive rectangular openings where thousands of containers stack vertically. Those openings weaken the structure in ways that require careful reinforcement elsewhere. Some naval architects compare the challenge to trying to build a giant hollow box that still behaves like a solid beam under stress. To compensate, shipbuilders strengthen certain critical sections using thicker steel and reinforced framing. The center of the ship often receives particular attention because it experiences enormous bending forces during heavy seas. When giant waves lift the bow and stern while the middle hangs lower, the hull experiences one type of stress. When the opposite happens, entirely different force patterns emerge. Engineers refer to these conditions as sagging and hogging. The terms sound almost harmless until you realize they involve a structure weighing hundreds of thousands of tons, flexing across hundreds of meters in open ocean. And despite all the reinforcement, these ships truly do bend. Not dramatically enough for passengers standing on deck to notice easily, but enough for engineers to measure carefully. In some conditions, the movement can become surprisingly significant. The sea essentially treats the vessel like a giant flexible object rather than a rigid machine. That reality changed how modern ships are built. Earlier generations of engineers often prioritized raw strength, making structures heavier and more rigid. But over time, researchers discovered that excessive rigidity could create its own dangers, because materials unable to flex appropriately may crack under repeated stress. This led to a more sophisticated understanding of fatigue and elasticity in ship structures. Modern container ships, therefore, rely partly on controlled flexibility. The hull must absorb energy rather than resisting every force absolutely. In a strange way, survival at sea often depends less on resisting motion and more on enduring it intelligently. The steel itself reflects this philosophy. Different sections of the ship use different grades depending on expected stress conditions. High tensile steel became increasingly important as ship sizes expanded because it allowed designers to maintain strength without adding excessive weight. Yet, stronger steel can also behave differently during welding and fatigue cycles. Every material decision creates new trade-offs somewhere else. Corrosion adds another layer of complexity. Salt water is relentless. Over years at sea, it attacks exposed metal continuously. Engineers therefore treat the hull almost like a living surface, constantly fighting environmental decay. Protective coatings cover much of the structure, including specialized marine paints designed to resist corrosion and reduce biofouling, the accumulation of algae, barnacles, and marine organisms on the hull. That buildup may sound minor, but even small increases in surface roughness can significantly increase drag over long voyages, forcing engines to burn more fuel. Some researchers estimate severe fouling can raise fuel consumption dramatically if maintenance is neglected. So even the paint on a container ship becomes part of a larger battle involving efficiency, physics, biology, and economics all at once. Deep inside the shipyard, workers continue assembling sections of the skeleton with astonishing precision. Welding crews move through narrow steel passages carrying sparks into unfinished compartments. The air often smells like heated metal, paint, oil, and seawater. In some areas, temporary lights cast long shadows across curved hull sections, making the interior feel less like a ship and more like the inside of an industrial cathedral. Certain compartments become so large and empty that voices echo several seconds after speaking. It is easy to forget while standing inside them that these hollow chambers will eventually cross entire oceans, carrying the physical heartbeat of global trade. Yet even here, surrounded by giant steel structures, tiny imperfections remain dangerous. Shipbuilders understand that stress rarely destroys vessels instantly. Catastrophic failures often begin invisibly. A microscopic flaw inside a weld, a poorly distributed force, a tiny crack hidden beneath layers of paint. Over years of vibration, waves, cargo loading, and temperature changes, small weaknesses can grow quietly until the structure finally reaches a breaking point. Maritime history contains several examples where structural failures shocked engineers because ships previously considered safe suddenly developed major cracks or even split apart under extreme conditions. Some incidents forced entire industries to rethink assumptions about metal fatigue and large-scale ship behavior. These lessons still influence modern shipbuilding today. That lingering fear of hidden weakness explains why inspection systems have become so advanced. Ultrasonic testing allows inspectors to search beneath the metal surface, for flaws invisible to the human eye. Sensors measure alignment continuously during assembly. Some newer ships even include structural monitoring systems capable of tracking stress patterns during real voyages. In a sense, the ship becomes a constantly monitored organism long after construction ends. Yet, despite all this technology, uncertainty never disappears completely. The ocean remains too complex, too dynamic, too indifferent to human engineering for total confidence. There is also growing discussion about whether container ships may eventually approach practical structural limits. Some engineers believe future advances in materials and design could allow even larger vessels. Others suspect the physics of long, flexible hulls may eventually become economically or structurally inefficient beyond certain scales. Larger ships place increasing demands on ports, canals, and infrastructure. More importantly, wave-induced stresses become increasingly complicated as dimensions expand. There may not be one single hard limit, but rather a gradual point where risks and costs begin outweighing efficiency gains. The debate continues quietly across the industry because global trade still rewards size aggressively. Every generation of megaship once seemed impossible before becoming normal, and perhaps that pattern itself creates pressure to keep pushing boundaries further. Sometimes the most fascinating part of these floating giants is not their power, but their vulnerability. Despite their enormous mass, they survive through delicate balances: weight distribution, structural flexibility, material behavior, buoyancy, stability, corrosion control. A modern container ship is less like a giant solid object and more like a carefully managed compromise held together by mathematics, engineering experience, and constant maintenance. Remove too much from that balance, and the ocean begins reclaiming control surprisingly quickly. Yet day after day, these vessels continue crossing some of the harshest environments on Earth, while carrying the systems modern civilization depends on almost invisibly. And eventually, once the skeleton is fully assembled, once the hull stands complete beneath the towering cranes, another transformation begins. Because until now, the ship has still been mostly silent steel, immense, complex, and powerful looking, but not yet truly alive. What changes that comes next? An engine so large and violent in its operation that it turns the entire vessel into something closer to a moving industrial organism than a traditional ship. Deep inside the finished skeleton of a mega container ship, beneath layers of steel decks and endless corridors of pipes and machinery, there is a space that feels completely different from the rest of the vessel. The cargo holds may feel vast and hollow. The outer decks may feel exposed and windswept. But the engine room feels alive, hotter, louder, denser. Even before the engines are switched on, the atmosphere changes the deeper you descend into the ship. Metal staircases vibrate faintly beneath your feet. Thick pipes run across the walls like industrial arteries. Massive ventilation systems hum continuously. The smell becomes a mixture of fuel, oil, seawater, heated steel, and machinery that is not yet fully awakened. And somewhere below all of it sits the true heart of the ship, one of the largest combustion engines humans have ever built. People often assume the biggest engines in the world belong to rockets, power plants, or giant mining machines. But some of the largest operating engines on Earth are hidden inside container ships crossing the oceans almost unnoticed by the public. Certain marine diesel engines rise several stories tall, weigh more than fully loaded passenger jets, and produce enough power to move entire floating cities across the Pacific Ocean for weeks at a time. Standing beside one for the first time reportedly creates a strange psychological effect because scale begins to break normal comparison. Pistons become taller than people. Crankshafts resemble industrial sculptures. Individual bolts require hydraulic equipment to tighten properly. The machinery stops feeling mechanical in the ordinary sense and starts feeling geological, as if part of the ship itself somehow evolved into a machine. One reason these engines became so enormous is efficiency. Unlike cars or aircraft, container ships travel slowly relative to their size. A megaship crossing the ocean may move at speeds around 20 knots, sometimes less during fuel-saving operations. That slower movement changes everything about engine design. Instead of prioritizing acceleration or compact size, marine engineers focus heavily on torque, reliability, and fuel efficiency over extremely long periods. Most large container ships use low-speed two-stroke diesel engines, a design that surprises many people because two-stroke engines are often associated with smaller machines like chainsaws or motorcycles. But large marine two-stroke engines operate very differently. Their enormous pistons move slowly compared to automotive engines, sometimes rotating at fewer than 100 revolutions per minute. Yet despite that relatively slow speed, the sheer scale of combustion inside each cylinder generates staggering power. Some cylinders alone are large enough for a person to stand inside during maintenance. Every combustion cycle releases controlled explosions powerful enough to turn propellers weighing dozens of tons beneath the ship. And unlike many land-based engines, these systems are designed to run continuously for astonishing lengths of time. During long voyages, marine engines may operate almost non-stop for weeks while crossing oceans, maintaining stable output through changing weather, temperature shifts, and varying sea conditions. Reliability, therefore, becomes almost sacred in marine engineering. Out in the middle of the Pacific, far from major ports, catastrophic engine failure is not merely inconvenient. It can become dangerous very quickly. This is why ship engines are built with extraordinary durability and extensive redundancy systems. Pumps, generators, cooling systems, lubrication systems, fuel systems, and backup controls surround the engine like support organs protecting a vital biological heart. The scale of fuel consumption alone reveals how different these ships are from ordinary transportation. Large container ships can consume enormous amounts of fuel per day, depending on speed and size. Although modern efficiency improvements have reduced consumption relative to cargo volume significantly compared to earlier generations. What makes container shipping remarkable is not that these vessels use small amounts of fuel overall. They absolutely do not. But that they move so much cargo simultaneously that the fuel cost per container often becomes surprisingly efficient compared to other forms of transportation. This efficiency helped make globalization economically possible on a massive scale. Yet, it also created uncomfortable environmental questions. Historically, many large ships relied on heavy fuel oil, a thick residual fuel sometimes compared in texture to tar when cold. It was cheap and energy-dense, but also heavily polluting. As environmental regulations tightened worldwide, the shipping industry entered a difficult transition period. Newer ships increasingly explore alternative fuels, such as liquefied natural gas, methanol, or lower sulfur marine fuels. Some researchers believe future vessels may eventually adopt entirely different propulsion systems. Others remain skeptical, arguing that replacing traditional marine fuels at global scale may prove slower and more complicated than public discussions sometimes suggest. The challenge is not merely technological. It involves infrastructure, fuel storage, energy density, economics, and international coordination across thousands of ports worldwide. Even now, engineers continue debating which fuel systems may dominate future shipping. And while environmental concerns reshape the industry, another engineering challenge remains brutally constant: vibration. When engines this large begin operating, the entire ship feels it. The power moving through the crankshaft transfers into the hull itself. Tiny oscillations spread through steel structures hundreds of meters long. Left uncontrolled, these vibrations could damage equipment, weaken structural components, or create dangerous resonance patterns throughout the vessel. Engineers therefore spend enormous effort managing vibration behavior. Flexible mountings, dampening systems, shaft alignment, and structural reinforcement all become essential. In some ways, the engine and the ship gradually become one connected mechanical organism. The propeller reveals this relationship perfectly. Hidden beneath the stern of the vessel sits one of the most important and strangely elegant components on the entire ship. Modern marine propellers can exceed 20 feet in diameter and weigh many tons. Yet their curved blades are shaped with extraordinary precision. Their design balances efficiency, cavitation control, vibration reduction, and durability. Cavitation itself becomes a fascinating problem. When propellers spin through water, pressure changes can create tiny vapor bubbles that collapse violently against the blade surfaces. Over time, this process can erode metal itself. Engineers therefore shape propellers carefully to minimize destructive cavitation while maximizing efficiency. Some newer propeller designs almost resemble sculpted artworks rather than industrial machinery. Their smooth curves hide years of hydrodynamic research beneath their polished bronze surfaces. The engine room also reveals something deeper about modern civilization. Much of the world depends on giant systems most people never see directly. Few consumers think about marine crankshafts while ordering products online. Few imagine combustion chambers larger than automobiles, powering the movement of global supply chains across dark oceans every night. Yet, without these engines, modern trade would slow dramatically. Entire economic systems quietly rely on machines hidden beneath steel decks thousands of miles offshore. There is something strangely invisible about maritime infrastructure, despite its enormous importance. And perhaps that invisibility partly explains why these engines feel almost mysterious when finally seen up close. They are simultaneously ordinary and extraordinary, common within the shipping world, yet almost unknown outside it. As megaships grew larger, engine manufacturers faced increasing pressure to produce more efficient systems without simply scaling size endlessly upward. Some experts believe modern marine engines may already operate surprisingly close to practical thermodynamic limits for combustion efficiency. Others argue future gains may come more from alternative fuels, digital optimization, waste heat recovery, or hybrid technologies than from traditional engine improvements alone. Certain experimental designs even revisit wind assistance through modern sail concepts or rotor systems, inspired partly by older maritime technologies. In a strange way, shipping innovation sometimes circles backward while moving forward. Ancient sailors depended entirely on wind. Modern megaships abandoned it almost completely. Yet, rising fuel costs and environmental pressures may slowly reintroduce aerodynamic assistance in advanced forms. Meanwhile, automation increasingly transforms engine operations themselves. Modern engine rooms contain extensive sensor networks constantly monitoring temperatures, pressures, fuel consumption, lubrication conditions, vibration levels, and mechanical performance. AI-assisted systems can help crews identify maintenance needs before failures occur. Some shipping companies already rely heavily on predictive maintenance models designed to reduce downtime and prevent catastrophic breakdowns. Yet despite all this technology, experienced marine engineers still play essential roles because machinery operating in harsh ocean environments rarely behaves perfectly predictably forever. Saltwater, heat, vibration, and continuous operation create endless opportunities for subtle problems to emerge. The sea continuously tests every mechanical assumption eventually, and perhaps nowhere does that become clearer than during storms. Because under calm conditions, even enormous engines can seem almost impossibly powerful and controlled. But when giant waves begin striking the hull, and the propeller occasionally lifts partially from the water during violent pitching, the relationship between engine and ocean becomes far more complicated. The ship starts shuddering differently. Loads shift unpredictably. Machinery strains against conditions impossible to reproduce fully inside any testing facility. In those moments, the engine no longer feels like a symbol of industrial dominance. It feels more like humanity's attempt to negotiate with forces vastly older and larger than itself. Maybe that is why marine engineers often speak about these engines with a mixture of pride and respect rather than simple confidence. They understand something most people rarely think about. Moving a floating steel city across an ocean is not normal. It only works because countless systems remain balanced almost perfectly for days or weeks at a time. And yet, they do work. Night after night, beneath container stacks towering above the deck, giant pistons continue rising and falling inside the darkness, pushing global trade across oceans with slow mechanical rhythm. If you were standing inside that engine room, hearing those massive cylinders fire one after another beneath layers of vibrating steel, what do you think would surprise you most? The size, the noise, or the realization that machines this enormous are quietly moving much of the modern world every single day? And despite all that power, there is one thing these ships can never fully control. Beyond the engine room walls waits the open ocean itself, where even the largest machines humanity has ever built still remain vulnerable once the storms begin. Out in the middle of the Pacific Ocean, far beyond the shipping lanes visible from land, a mega container ship can begin to feel strangely isolated from the rest of humanity. During calm weather, the voyage may appear almost mechanical. The engines pulse steadily beneath the decks. Containers remain stacked in perfect geometric rows. Navigation screens glow quietly inside the bridge, while the ship cuts through dark water with slow, controlled momentum. But the ocean has a way of changing personality with almost no warning. A pressure system deepens somewhere beyond the horizon. Wind shifts direction. Swells begin arriving from multiple angles. The sky slowly disappears behind layers of thickening clouds. And then, somewhere inside the steel body of a 400-meter vessel carrying thousands of containers and billions of dollars in cargo, everyone on board becomes aware of the same unsettling reality at once. Despite all the engineering, all the simulations, all the power hidden inside the engine room, the ship is about to enter an environment no machine ever fully controls. One of the strangest misconceptions about mega container ships is the belief that their enormous size makes them almost immune to storms. Intuitively, it sounds reasonable. A vessel larger than many skyscrapers should feel stable compared to smaller boats. And in some conditions, size absolutely helps. Larger ships generally handle many types of waves more smoothly than smaller vessels. But size also introduces new vulnerabilities that become increasingly serious as ships grow longer and heavier. A 400-meter container ship does not simply ride over the ocean like a floating building. It becomes part of the motion of the sea itself. Waves interact with different sections of the hull simultaneously. The bow may climb upward while the stern drops into a trough. Seconds later, the entire pattern reverses. The ship begins bending continuously across its length, almost like a giant steel spine twisting under pressure. Crew members inside these vessels sometimes describe storms not as violent shaking, but as slow, overwhelming motion. The sensation that the entire structure is flexing around you, while enormous invisible forces move through the steel beneath your feet. Modern container ships are carefully designed to survive these stresses, but the forces involved can still become extraordinary. During severe weather, waves may exceed heights comparable to multi-story buildings. Water crashes against the hull with impacts strong enough to damage equipment or deform steel structures under certain conditions. The bow occasionally disappears beneath heavy seas before rising again through exploding spray and foam. On the bridge, visibility may collapse into darkness, rain, and moving walls of water, illuminated only by navigation lights and lightning. Yet some of the most dangerous forces during storms are not always the obvious ones. They are the hidden stress patterns developing silently inside the ship itself. Because container ships are so long, they experience something naval architects call torsion, twisting forces created when different sections of the vessel encounter waves from varying directions. Imagine holding a giant metal ruler and slowly twisting opposite ends in different directions. Now imagine doing that repeatedly to a structure carrying tens of thousands of tons across an unpredictable ocean. The larger the ship becomes, the more difficult these torsional forces become to manage. Engineers spend years studying how hulls respond to wave patterns because, under certain conditions, the ocean can accidentally synchronize with the ship's natural movement frequencies. When this happens, rolling and structural stress may intensify dramatically through resonance effects. Most voyages never encounter the worst possible combinations, but the possibility remains real enough to influence design decisions constantly. There are also waves the ocean still does not fully explain. Rogue waves, sometimes called freak waves, have long occupied a strange space between maritime folklore and scientific observation. For centuries, sailors described enormous isolated waves appearing suddenly in otherwise manageable seas. Many experts once dismissed such stories as exaggerations, but satellite observations and modern measurements eventually confirmed that rogue waves do exist. Exactly how frequently they occur remains debated, but some documented examples reached heights capable of threatening even large modern vessels under the wrong conditions. Researchers believe certain wave interactions may concentrate energy unexpectedly into single massive waves, although the full mechanics remain complex and still actively studied. For crews aboard container ships, the possibility of encountering one adds another layer of uncertainty to ocean travel. Because storms are not only about wind and rain, they are about unpredictability itself. And unpredictability becomes especially dangerous when combined with cargo stacked high above the deck. Modern megaships can carry more than 20,000 containers. Each one must be carefully secured using locking systems and structural supports designed to resist shifting during rough seas. Yet containers occasionally break free anyway. In heavy storms, violent rolling motions may place enormous stress on container stacks. Once a few containers shift or collapse, chain reactions can occur surprisingly fast. Entire rows may topple overboard into the ocean. Some incidents have resulted in hundreds of containers lost during single storms. And because containers carry everything from electronics to chemicals to industrial materials, the consequences extend beyond financial loss. Certain cargoes become environmental hazards once released into the sea. Others create navigational dangers for nearby ships if containers remain partially floating beneath the surface. Shipping companies continuously improve securing systems, loading strategies, and weather routing, partly because these losses remain difficult to eliminate entirely. Cargo distribution itself becomes critical during storms. Weight must remain balanced carefully throughout the vessel. A container placed in the wrong location may not seem important individually, but collectively, cargo distribution dramatically affects stability. This is why modern ships rely heavily on sophisticated loading software that calculates how weight spreads across the hull. Containers carrying dangerous materials often require special placement. Refrigerated containers need electrical systems. Heavier cargo usually stays lower in the ship to maintain stability. Everything becomes part of a giant floating equation, constantly changing from port to port. And even then, uncertainty remains. There have been cases where incorrect cargo weight declarations contributed to instability problems because containers turned out heavier than reported. A few hidden tons, repeated thousands of times, can quietly alter how a ship behaves at sea. Ballast systems help manage part of this problem. Deep inside the hull, ships carry enormous ballast tanks filled with seawater. By adjusting ballast levels, crews can influence trim, balance, and stability depending on cargo conditions and sea state. In rough weather, proper ballast management becomes essential because the ship must maintain enough stability to resist dangerous rolling while also avoiding excessive structural stress. Yet ballast water created another unexpected issue over time: ecological disruption. Organisms transported unintentionally between regions inside ballast tanks sometimes invaded entirely new ecosystems after discharge at distant ports. Some marine biologists consider ballast transfer one of the major pathways for invasive aquatic species worldwide. So even the hidden stabilization systems of container ships quietly reshape global environments in ways few people think about. Meanwhile, inside the storm itself, human experience aboard the vessel changes dramatically. Walking becomes difficult as the deck tilts rhythmically beneath every step. Metal groans echo through the structure. Loose equipment rattles constantly. Sleeping may become nearly impossible during severe rolling. The ship does not move like a car or airplane. It moves slowly, massively, with delayed momentum that can feel deeply unnatural to the human body. Some crew members adapt over years at sea. Others never fully do. Yet, despite the discomfort and danger, modern crews continue navigating conditions that earlier generations of sailors would have considered terrifying aboard vessels this large. Technology helps, of course. Weather forecasting improved enormously in recent decades. Satellite systems track storm development with increasing accuracy. Routing software helps ships avoid the worst conditions when possible. But avoidance is not always practical. Shipping schedules, fuel economics, port timing, and geography sometimes force vessels into difficult weather regardless. Certain routes, especially across the North Pacific or North Atlantic during winter, are infamous for brutal sea states. Mariners operating there know the ocean can still humble even the most advanced ships on Earth. And perhaps that is the deeper reality storms reveal. Mega container ships often symbolize industrial power, globalization, and engineering triumph. They appear almost invincible while docked in ports beneath towering cranes. But far from land, inside heavy weather, those illusions begin fading. The ship becomes something else entirely. Not a machine dominating nature, but a fragile, moving balance trying to survive within it. Every wave reminds the crew that the ocean does not care about cargo schedules stock markets, or supply chains. It follows older rules. Sometimes the vessel wins that negotiation smoothly. Sometimes it barely does. And occasionally, despite all precautions, the sea still finds weaknesses. There have been ships damaged severely by storms, cracked by structural stress, or crippled by cargo failures under extreme conditions. Rarely, vessels have even broken apart entirely after encountering combinations of weather and structural fatigue engineers never fully anticipated. These incidents remain uncommon compared to the vast scale of global shipping, but they continue shaping maritime engineering because every failure forces difficult questions about limits. How large can ships safely become? How much stress can materials truly endure after decades at sea? At what point does efficiency begin competing dangerously against resilience? There are no perfectly settled answers. What is certain is that every mega container ship crossing an ocean carries within it a quiet gamble between human engineering and environmental uncertainty. Most voyages end uneventfully. Some become stories crews never forget. And somewhere beyond the storm clouds, beyond the bending steel and crashing water, another challenge still waits ahead. Because even after surviving the open ocean, the ship eventually reaches the crowded ports where thousands of containers must somehow be unloaded, sorted, and moved with astonishing precision before the entire cycle begins again. ID 51634. When a mega container ship finally approaches one of the world's largest ports after weeks at sea, the scene often feels less like transportation and more like the arrival of a moving industrial ecosystem. Long before the vessel reaches the dock, tugboats begin circling nearby. Giant cranes stand waiting along the shoreline like mechanical towers frozen against the sky. Thousands of containers stacked across the deck rise above the waterline in endless geometric rows, each one carrying pieces of someone else's life somewhere across the planet. Electronics from East Asia, machinery parts from Europe, furniture, clothing, chemicals, food, medical equipment, batteries, toys, construction materials. Looking at the ship from a distance, the cargo almost appears random. But nothing about modern container shipping is random anymore. Behind those perfectly stacked metal boxes lies one of the most complicated logistical systems humans have ever created. Because the deeper the shipping industry expanded, the more engineers discovered that moving cargo efficiently was no longer mainly about building larger ships. It became about organizing unimaginable complexity without allowing the entire system to collapse into chaos. A modern mega container ship may carry more than 20,000 containers at once. If those containers were placed end to end, they could stretch for well over 100 miles. And yet, every single one must occupy an exact position, calculated before the ship even leaves port. Weight distribution, destination sequence, hazardous cargo separation, refrigeration access, structural stress, balance, crane efficiency, unloading order, fuel economy, weather stability, and even emergency access all influence where each container can be placed. To outsiders, Container stacks may look like giant piles of boxes arranged neatly for convenience. In reality, they behave more like a constantly changing three-dimensional puzzle where every mistake can create expensive or dangerous consequences later in the voyage. One of the first challenges begins with weight itself. Containers are not all equally heavy. Some carry lightweight consumer goods. Others contain dense industrial materials weighing tens of thousands of pounds. If heavy containers are distributed incorrectly, the ship's stability changes dramatically. Too much weight high above the deck can increase rolling risk during storms. Uneven loading across the hull may place dangerous stress on the structure itself. Modern loading systems therefore rely heavily on specialized software, capable of calculating how forces spread throughout the vessel based on cargo placement. In some ways, every loaded container becomes part of the ship's structural behavior at sea. And because megaships have grown so large, even relatively small loading errors repeated thousands of times can quietly shift the vessel's balance into dangerous territory. There have been incidents where incorrect cargo weight declarations contributed to serious stability problems because containers turned out significantly heavier than reported. After several accidents raised concerns, international regulations increasingly pushed for verified container weights before loading. Yet, enforcing complete accuracy across global supply chains remains difficult because shipping networks involve countless companies, ports, and subcontractors operating under intense economic pressure. Speed matters enormously in modern logistics. Ports are expensive. Delays cost money rapidly. Mega ships, therefore, attempt to minimize time spent docked because every extra hour affects schedules across entire shipping networks. This urgency transformed ports into highly choreographed industrial environments where giant cranes unload and reload containers almost continuously. Some modern cranes can move containers with astonishing speed, lifting steel boxes weighing many tons high into the air, while operators guide them with precision that borders on surreal. Watching these cranes work at night beneath floodlights can feel strangely futuristic. Containers drift silently above the dock, while automated vehicles below move in carefully controlled patterns, like pieces inside a giant machine. In certain advanced ports, automation now handles significant portions of cargo movement. Driverless transport vehicles carry containers between cranes and storage areas using navigation systems coordinated by central software. Sensors track container locations constantly. AI-assisted logistics systems help optimize storage arrangements and loading schedules based on future departures. Some analysts believe ports may become increasingly autonomous in coming decades, although full automation remains controversial, partly because of labor concerns and the unpredictable complexity of real-world shipping operations. Even with advanced systems, ports still depend heavily on human oversight, because unexpected situations happen constantly. Weather changes, equipment fails, containers arrive late, cargo declarations contain errors, mechanical breakdowns interrupt schedules. The scale of modern shipping leaves surprisingly little room for disruption before delays begin spreading outward through supply chains. What makes container loading particularly fascinating is that unloading order matters almost as much as loading itself. A ship rarely travels between only two locations. Instead, it may stop at multiple ports across different countries during a single voyage. Containers intended for earlier destinations must remain accessible without forcing crews to move countless others unnecessarily. This means cargo planners essentially design temporary architectural structures where future access patterns become part of the stacking strategy. A container placed incorrectly may require expensive reshuffling operations later, slowing the entire port process dramatically. The ship, therefore, carries not only cargo, but a carefully sequenced map of future unloading events spread across oceans and continents. Refrigerated containers add another layer of complexity. Known as reefers, these containers transport temperature-sensitive cargo, such as food, pharmaceuticals, and medical supplies. Unlike ordinary containers, reefers require continuous electrical power during voyages. Ships therefore include extensive power systems connected throughout designated cargo areas. A failure affecting reefer containers can quickly become extremely costly if cargo spoils. Some vessels carry thousands of refrigerated containers simultaneously, effectively operating giant floating cold storage networks across oceans. Hazardous cargo introduces still more complications. Certain chemicals, fuels, batteries, or reactive substances cannot safely sit near one another. International regulations specify detailed separation requirements for dangerous goods because fires aboard container ships remain among the most feared maritime emergencies. Fighting large fires at sea is extraordinarily difficult, even on modern vessels. Containers stacked high above the deck create dangerous conditions where heat, wind, and limited access complicate firefighting efforts severely. Some cargoes can react unpredictably once ignited. Lithium-ion batteries, especially, became growing concerns in recent years because thermal runaway events may spread rapidly under certain conditions. Several major ship fires forced investigators to examine whether increasing cargo complexity was outpacing traditional safety systems. There is ongoing debate about whether current regulations fully account for the scale and variety of modern containerized trade. Some experts argue container inspection systems remain imperfect because ports simply process too much cargo too quickly for exhaustive verification. Others believe future technologies such as advanced scanning or AI-driven monitoring may improve safety significantly over time. Yet, uncertainty persists because global trade now moves at extraordinary speed and scale. One incorrectly declared container, hidden among thousands, may remain unnoticed until something goes wrong far out at sea. The physical process of stacking containers also affects the ship aerodynamically. On megavessels, container stacks can rise many stories above the deck, creating enormous wind surfaces during storms. Engineers and cargo planners therefore consider not only weight, but also how wind forces interact with the loaded ship. In certain conditions, high container stacks may influence rolling behavior or increase structural stress. Again, The vessel behaves less like a simple cargo carrier and more like a constantly changing physical system, adapting to every voyage differently. Even fuel efficiency connects back to loading strategies. Proper balance and trim reduce drag through the water. Poor loading may increase resistance subtly but significantly over long distances. Modern shipping companies therefore analyze cargo distribution partly through the lens of operational efficiency, because even minor fuel savings become financially meaningful across global fleets. In many ways, the real genius of container shipping lies not in the containers themselves, but in standardization. Every container follows internationally recognized dimensions, allowing ships, trains, trucks, cranes, warehouses, and ports worldwide to interact almost seamlessly. That standardization created one of the most successful logistical systems in human history. Yet it also produced a strange side effect: invisibility. Most people rarely think about the containers surrounding their daily lives. They see products arriving in stores, but not the giant synchronized networks carrying those products across oceans continuously. Somewhere out there tonight, thousands of container ships are moving silently through darkness, while ports operate around the clock to keep global trade flowing without interruption. And beneath the apparent order of that system lies constant tension between efficiency and fragility. The larger and faster shipping became, the more dependent modern economies grew on uninterrupted logistics. Delays that once seemed minor can now ripple through supply chains worldwide. A congested port, a labor dispute, a storm, a ship accident. One disruption may suddenly affect factories, retailers, transportation networks, and consumers across multiple countries simultaneously. In some ways, mega container ships reveal how interconnected modern civilization truly became. The cargo inside them is not separate from ordinary life. It is ordinary life, moving in steel boxes across the ocean. Perhaps that is why ports feel strangely cinematic at night. Floodlights reflect off rows of containers stretching into darkness, while cranes continue lifting cargo with mechanical precision hour after hour. The ship stands there silently, absorbing and releasing entire fragments of the global economy before preparing to leave again. And eventually, once the final containers lock into place and the loading calculations confirm stability, another phase begins. The vessel slowly pulls away from the dock, carrying thousands of carefully arranged steel boxes toward another ocean crossing. But before the journey truly begins, there is still one moment every engineer and captain watches closely. The first time the completed ship fully returns to open water under its own power, where no simulation or loading plan can completely predict how reality will respond. For months, sometimes years, the ship existed inside a world of steel, cranes, welding sparks, and dry concrete. Workers walked beneath its hull while it rested motionless inside the dock, like a sleeping industrial giant waiting for permission to become real. Every pipe, cable, engine component, ballast tank, and structural beam had been installed under conditions engineers could still mostly control. Measurements were checked constantly. Simulations predicted how the vessel should behave. Stress calculations estimated how the structure would distribute force once floating. But despite all the technology involved, there remained one truth nobody inside the shipyard could fully escape. Until the vessel actually touched open water for the first time, much of its future still existed, partly in theory. And that is what makes launch day feel so different from every earlier stage of construction. It is the moment the ship stops being an object engineers build and starts becoming something the ocean will judge for itself. From a distance, launch ceremonies often appear calm and ceremonial. Flags hang from railings. Executives and officials gather near the dock. Cameras wait along the shoreline. Speeches may celebrate engineering achievement, international trade, or the future of the shipping industry. Traditionally, some launches still include ceremonial champagne bottles broken against the hull, a ritual with roots stretching deep into maritime history. Yet beneath the public celebration, the atmosphere among shipbuilders tends to carry a different emotional weight entirely, because everyone involved understands that moving a structure this large into water is not merely symbolic. It is one of the most delicate and potentially dangerous moments in the entire construction process. Historically, ship launches sometimes ended catastrophically when calculations failed or structures behaved unexpectedly. Even today, despite modern engineering precision, launching a megaship remains a carefully controlled operation where enormous mass suddenly begins moving under the influence of gravity, buoyancy, momentum, and water pressure all at once. Some older launch methods looked almost violent. In traditional side launches, ships slid sideways into the water from ramps along the shoreline. Watching archival footage of massive vessels entering the sea this way still feels shocking. Entire hulls would suddenly accelerate downward before crashing into the water with explosive force, throwing enormous waves outward across the harbor. Spectators often gathered surprisingly close, considering the risks involved. Several historical launches caused injuries or damage when vessels behaved unpredictably during entry. Modern mega-container ships, however, became so large that side launches often stopped being practical or safe. Instead, many are now floated out gradually from dry docks. The process appears calmer visually, but the engineering tension remains intense because the ship's entire relationship with physics changes the moment buoyancy begins supporting its weight instead of the dock beneath it. As water slowly enters the dry dock, workers monitor countless systems continuously. Sensors track alignment and pressure. Engineers watch for unexpected stress patterns. Pumps operate constantly. Tugboats stand ready nearby. Slowly, almost imperceptibly at first, the vessel begins transferring its weight onto the surrounding water. For the first time, the hull flexes exactly as it was designed to at sea. Tiny movements ripple through the structure. Internal forces redistribute. Steel sections that previously rested against solid support now experience entirely different loading conditions. This transition matters enormously because even small miscalculations could reveal hidden structural weaknesses. Some engineers reportedly describe these moments with unusual honesty. Despite all the simulations, there is always a brief period where everyone watches carefully to see whether reality agrees with the math. And sometimes reality behaves differently than expected. Certain problems only reveal themselves once the ship floats freely for the first time. Minor alignment issues, unexpected vibration patterns, leaks, electrical faults, stability irregularities. Most are manageable, but their appearance reminds everyone that computer models, no matter how sophisticated, still simplify the complexity of the real world. Water itself behaves unpredictably at large scales. Massive steel structures respond dynamically. Tiny tolerances multiply across hundreds of meters. The launch, therefore, becomes less like flipping a switch and more like waking a sleeping organism, slowly enough to notice whether anything feels wrong. Once fully afloat, the ship enters another strange phase of existence. It is technically in the water now, but not yet truly complete. Tugboats guide it carefully through the harbor, while crews continue working on board. Construction equipment may still remain inside certain compartments. Some systems have not undergone full operational testing yet. The vessel looks finished from the outside, but internally, many details still require calibration, inspection, and adjustment before ocean trials begin. In a sense, the ship exists temporarily between two worlds. No longer a construction project, but not fully a working vessel either. And this transitional stage may reveal something deeper about modern engineering itself. Giant systems rarely emerge fully complete all at once anymore. They evolve through layers of testing, adaptation, and gradual activation. The sea trials that follow launch become crucial because this is the first time the ship truly experiences motion under its own power. Engines start pushing against open water. The propeller begins transferring force through the hull. Navigation systems activate fully. Crews test steering, acceleration, emergency systems, communication equipment, radar, fuel systems, ballast controls, and countless other functions under real operating conditions. During these trials, the vessel may perform sharp turns, speed tests, stopping maneuvers, and stability evaluations that appear almost strange for something so enormous. Watching a mega container ship execute controlled movements during testing can feel surreal because the scale conflicts with the precision. It moves like an industrial continent, somehow learning to steer itself. One of the most closely watched aspects during sea trials is vibration behavior. Engineers already modeled expected patterns extensively before launch, but real conditions often reveal additional complexities. Resonance problems can emerge unexpectedly when engine frequencies interact with structural behavior under certain speeds or sea states. Even relatively minor vibration issues matter because they may create long-term fatigue problems over years of operation. Crews therefore collect enormous amounts of performance data during these voyages, comparing reality against earlier simulations carefully. Fuel efficiency testing also becomes critical. Modern container shipping operates on thin economic margins, where even small efficiency improvements matter significantly over long distances. Engineers analyze how the hull behaves at various speeds, how much fuel the engines consume under different loads, and whether the vessel performs according to design expectations. Some ships exceed predictions, others require adjustments after trials reveal subtle inefficiencies. Real conditions often reveal something deeper about modern engineering itself. Some ships exceed predictions, others require adjustments after trials reveal subtle inefficiencies. weather conditions during testing can strongly influence results too, adding another layer of uncertainty. And despite all the engineering sophistication surrounding launch and trials, there remains something emotionally strange about the first voyage under open sky. The ship finally leaves the artificial environment of the yard and enters the same oceans that challenged sailors for thousands of years before containerization ever existed. The cranes disappear behind the horizon. The harbor grows distant. Wind, currents, waves, and weather begin interacting with the vessel naturally rather than theoretically. Perhaps this is why experienced shipbuilders often describe launch day less as a celebration and more as a moment of release. After years controlling every measurable detail, they hand the vessel over to environments they can never fully control again. In some ways, the ocean becomes the final engineer. What makes mega container ships particularly fascinating during this stage is how fragile their balance actually is, despite their immense size. To the public, these vessels often symbolize industrial confidence and technological mastery. But internally, crews and engineers know the truth is more complicated. The ship survives because thousands of interconnected systems continue functioning together correctly. Ballast levels, cargo distribution, engine performance, structural flexibility, navigation decisions, weather routing, human judgment. Remove enough pieces from that balance and the illusion of invulnerability disappears surprisingly fast. This realization became especially visible in recent decades as global shipping pushed vessels toward increasingly extreme dimensions. Some analysts argue modern megaships represent the peak of logistical efficiency. Others quietly wonder whether the industry may already be approaching practical limits, where size introduces vulnerabilities faster than benefits. Larger ships require deeper ports, taller cranes, narrower operating margins, and increasingly complex infrastructure. They also concentrate massive amounts of global trade into fewer individual vessels. One mechanical failure or navigational problem involving a single megaship can now affect supply chains across continents. The launch of each new vessel, therefore, carries a subtle question hidden beneath the celebration. Are humans building the future of global trade, or slowly constructing systems too large and interconnected to fail safely? There is no universal agreement, but perhaps that uncertainty is part of what makes these ships feel so compelling. They embody both extraordinary engineering success and the growing complexity of the modern world itself. And eventually, once the sea trials end and the final inspections are approved, the ship officially joins the global fleet. The floating steel city that once existed only as digital models and unfinished blocks inside the yard now begins crossing oceans for real. But the deeper it enters the world's shipping networks, the more another reality emerges. These vessels are no longer simply transportation machines. They are becoming central pieces of a global system so interconnected that when one ship encounters trouble, entire economies can sometimes feel the effects. For decades, the world treated larger container ships as symbols of progress. Every new generation arrived with longer hulls, taller container stacks, and greater carrying capacity than the last, ports celebrated their arrival. Shipping companies competed aggressively to build them. Governments expanded canals and deepened harbors to accommodate them. And for a long time, the logic seemed almost undeniable. Bigger ships lowered transportation costs. Lower transportation costs accelerated global trade. Global trade fueled economic growth. The system appeared to reward scale endlessly. But slowly, almost quietly at first, another pattern began emerging beneath the optimism. The ships were not only adapting to the world anymore, the world itself was beginning to reshape around the demands of the ships. And the larger these vessels became, the more pressure they started placing on ports, coastlines, supply chains, ecosystems, labor systems, and even the fragile timing mechanisms of the global economy itself. One of the clearest examples appeared at ports. Modern mega container ships require infrastructure so enormous that many older ports simply cannot handle them. The channels leading into harbors must be dredged deeper to accommodate their draft. Bridges sometimes become clearance hazards because container stacks rise extraordinarily high above the waterline. Cranes must grow taller and extend farther outward to reach containers stacked across decks wider than previous generations of vessels. Entire terminal systems require redesigning because unloading 20,000 containers efficiently demands levels of coordination older ports were never designed to support. In some regions, billions of dollars have been spent modernizing ports specifically to remain competitive in the era of megaships. Cities that fail to adapt risk becoming less relevant in global trade networks. This created a strange reversal in power. Historically, ships adapted themselves to the limitations of ports and waterways. Increasingly, ports now reshape themselves around the dimensions of the ships instead. The Panama Canal offers one of the clearest illustrations of this shift. For decades, the canal imposed strict limits on vessel size, creating the famous Panamax classification. Entire generations of ships were designed specifically to fit through it. But as container ships kept growing, pressure mounted to expand the canal itself. The massive expansion project completed in 2016 allowed larger vessels to pass through, fundamentally changing trade routes and shipping economics once again. The Suez Canal faced similar pressures as global shipping volume intensified. Yet every expansion creates another cycle. Once canals and ports adapt, shipbuilders push sizes further again because larger ships still promise competitive advantages under certain market conditions. It becomes a moving target where infrastructure and vessel design continuously chase each other forward. But this escalating scale also increases fragility in ways that became dramatically visible during the Ever Given incident in 2021. When the enormous container ship became lodged sideways inside the Suez Canal during high winds and difficult navigation conditions, global trade suddenly experienced something few people had fully considered before. One ship had effectively disrupted a major artery of world commerce. Hundreds of vessels backed up behind it. Delays spread outward through international supply chains. Manufacturers, retailers, and shipping networks across continents felt the consequences almost immediately. The image itself became strangely symbolic. a gigantic modern vessel immobilized in one of the world's most important waterways, exposing how dependent global systems had become on uninterrupted maritime movement. Analysts debated exactly how much the blockage cost the global economy, but what mattered more was the realization it triggered. Megaships had become so large and so central to global trade efficiency that individual incidents now carried enormous systemic consequences. Some experts argued the event represented a warning about over-concentration within modern logistics. Others believed it was simply a rare accident, amplified by media attention. But either way, the incident forced broader public awareness of something maritime industries already understood. The global economy increasingly depends on giant interconnected systems operating with very little margin for disruption. And those disruptions do not always begin dramatically. Sometimes they begin with congestion. Modern megaships unload extraordinary amounts of cargo at once. While this improves transportation efficiency during voyages, it can overwhelm ports once the ship arrives. Thousands of containers suddenly flood terminals, truck networks, rail systems, and storage facilities simultaneously. During periods of strong consumer demand or logistical imbalance, ports may struggle to process incoming cargo quickly enough. Containers accumulate. Ships wait offshore. Truck shortages develop. Warehouses fill beyond capacity. The COVID-era supply chain disruptions revealed how vulnerable these interconnected systems could become under stress. Images of dozens of container ships anchored outside major ports, waiting for unloading, became symbols of a deeper issue. Modern logistics systems had become optimized heavily for efficiency, but perhaps not always for resilience. Some economists and logistics experts began questioning whether decades of relentless efficiency optimization inadvertently reduced flexibility within global supply chains. Megaships contributed to that conversation because they concentrate massive amounts of cargo movement into fewer arrivals. If everything works smoothly, the system becomes highly efficient. If something fails, bottlenecks grow rapidly. Environmental concerns add another layer of pressure surrounding these ships. Despite being relatively efficient per container compared to many transportation methods, mega container ships still rely heavily on fossil fuels and contribute significantly to global emissions overall. Because of the enormous scale of maritime trade, the shipping industry faces increasing international pressure to reduce carbon output, sulfur emissions, and environmental impact. New fuel standards, alternative propulsion technologies, and efficiency regulations continue reshaping ship design. Yet transitioning global shipping away from traditional fuels remains extraordinarily difficult. Large vessels require immense energy density to cross oceans economically. Batteries alone currently struggle to provide practical, long-range solutions at these scales. Alternative fuels such as methanol, ammonia, hydrogen, or liquefied natural gas each introduce advantages and complications. Some experts believe the future may involve multiple technologies evolving simultaneously rather than one dominant replacement. Others warn that environmental regulation could eventually reshape global trade itself if transportation costs rise significantly. There is also the issue of underwater noise pollution, a problem most people rarely think about. Mega ships generate continuous low-frequency sound through engines, propellers, and hull vibration. Marine biologists increasingly study how this noise affects whales and other marine species that rely on sound for navigation and communication. Propeller cavitation alone creates enormous underwater acoustic disturbances across heavily trafficked shipping routes. Some researchers suspect chronic shipping noise may alter migration patterns or stress marine ecosystems in ways not yet fully understood. The oceans may appear empty from above, but beneath the surface, they are already crowded with invisible industrial sound. Ballast water creates additional ecological concerns. Organisms transported unintentionally between continents can invade entirely new ecosystems once ballast water is discharged. Zebra mussels, invasive algae, and countless smaller marine species spread partly through global shipping networks. International regulations now require ballast treatment systems on many vessels, but the issue revealed another hidden truth about container shipping. These ships do not simply move products, they move environmental consequences across the planet as well. Even labor patterns changed under the pressure of megaships. Automation accelerated rapidly at ports, partly because handling modern cargo volumes efficiently became increasingly difficult through traditional, labor-intensive methods alone. Some terminals now operate with surprisingly small human crews, relative to the scale of cargo movement occurring. Automated cranes, AI-driven scheduling systems, autonomous transport vehicles, and predictive logistics software continue reshaping port operations. Supporters argue automation improves efficiency and safety. Critics worry about labor displacement and overdependence on complex technological systems vulnerable to cyber attacks or software failures. Maritime cybersecurity itself became a growing concern as shipping networks digitized further. Modern ports and ships rely heavily on interconnected digital systems for navigation, cargo management, communication, and logistics coordination. Some analysts quietly warn that future disruptions may not come only from storms or accidents, but from malicious attacks targeting critical infrastructure hidden behind global trade networks. Perhaps the deeper question emerging around megaships is not whether they work. Clearly, they do. Modern civilization depends on them every day. The real question may be whether systems built primarily around maximum efficiency eventually create new forms of vulnerability difficult to recognize until something breaks. Historians often note that complex systems throughout history tend to appear stable right before periods of disruption, because their internal dependencies become difficult to see while everything functions normally. Global shipping today sometimes carries that same feeling. The system operates with astonishing sophistication and reliability most of the time. Yet its scale and interdependence also mean disruptions now spread farther and faster than ever before. There is no broad consensus about where these trends ultimately lead. Some experts believe shipping networks will continue adapting successfully through new technologies, smarter logistics, greener fuels, and more resilient infrastructure. Others suspect the era of endlessly larger ships may eventually slow as costs, risks, and environmental pressures increase. Certain analysts even argue future trade patterns could become more regionalized rather than fully globalized under geopolitical tension or climate pressure. But for now, mega container ships continue growing into some of the most important moving structures on Earth. They connect economies, industries, and consumers across oceans almost invisibly. And perhaps that invisibility remains the most fascinating part of all. Most people never think about the ships carrying the physical framework of modern life until something goes wrong. A blockage, a shortage, a delay, a storm. Suddenly, the hidden machinery of globalization becomes visible for a moment. Then, once the disruption fades, the giant vessels quietly continue moving again across dark oceans under the night sky. Yet, somewhere within the industry, another question continues growing louder. If these ships already reshape ports, economies, ecosystems, and global infrastructure at their current size, what happens if the next generation becomes even larger still? Late at night, somewhere far out in the Pacific, a modern container ship can look almost unreal. Thousands of containers sit stacked above the deck in perfect rows, while navigation lights glow against the darkness like a floating industrial skyline drifting silently across the ocean. Deep beneath the hull, engines continue turning with slow mechanical rhythm. Radar systems sweep the horizon continuously. Satellite links exchange invisible streams of data with ports thousands of miles away. And inside the bridge, only a surprisingly small number of people may be awake, guiding one of the largest moving structures humans have ever built through open water, while much of the world sleeps, completely unaware of it. In many ways, container ships already feel like machines from the future. Yet, inside the shipping industry, there is growing recognition that these vessels may still represent only the beginning of a much larger transformation. Because the forces now shaping global shipping, climate pressure, automation, artificial intelligence, energy transitions, geopolitical instability, and rising infrastructure demands, are beginning to push the next generation of ships into territory that once sounded almost impossible. For decades, the shipping industry focused heavily on one primary idea: bigger ships create greater efficiency. But now, the future appears far less certain. Some engineers believe container ships may continue growing larger. Others suspect the era of endless expansion may be approaching practical limits imposed by physics, economics, or infrastructure itself. And quietly, another possibility has started emerging beneath those debates. Perhaps the future of shipping will not depend solely on size anymore, but on intelligence. One of the most dramatic changes already underway involves automation. Modern container ships rely heavily on digital systems compared to earlier generations. Navigation software assists route planning. Sensors monitor engine performance continuously. AI-driven systems analyze fuel efficiency, weather conditions, cargo distribution, and maintenance schedules. Some shipping companies now use predictive algorithms capable of identifying mechanical problems before crews even notice symptoms directly. But future vessels may go much further. Several companies and research groups are already exploring partially autonomous or remotely operated cargo ships. The idea sounds futuristic, yet the underlying logic is straightforward. Modern ships already depend heavily on automated systems, and reducing crew size could lower operational costs while potentially minimizing certain human error risks. Smaller crews also free additional space for cargo or equipment. Some prototype autonomous vessels have already completed limited test operations under controlled conditions. But full autonomy at ocean scale remains deeply controversial. Oceans are unpredictable environments filled with storms, equipment failures, crowded shipping lanes, piracy risks, and countless unusual situations difficult for software to anticipate perfectly. Experienced mariners often point out that much of navigation still depends on judgment rather than rigid procedure alone. A captain may interpret subtle weather behavior, mechanical sounds, or developing situations in ways difficult to reduce into algorithms completely. Supporters of autonomous shipping argue artificial intelligence will continue improving rapidly. Critics counter that oceans punish overconfidence harshly, and removing human adaptability from complex maritime environments may create new risks rather than eliminating old ones. There is no clear consensus yet. What seems more likely in the near future is a gradual increase in hybrid systems, where human crews work alongside increasingly sophisticated automation rather than disappearing entirely. Fuel may become an even larger challenge than automation. For over a century, global shipping relied primarily on fossil fuels because they provided unmatched energy density for long ocean voyages. But climate concerns and international emissions regulations are now forcing the industry toward difficult choices. Shipping contributes a significant share of global greenhouse gas emissions overall, especially considering the scale of worldwide maritime trade. Governments and international organizations continue pressuring the industry to reduce carbon output dramatically over coming decades. The problem is that replacing traditional marine fuel systems at massive scale is extraordinarily complicated. Batteries alone currently struggle to power giant vessels across oceans economically because energy storage requirements become enormous. Hydrogen shows potential, but introduces difficult storage and infrastructure challenges. Ammonia attracts growing attention because it carries no carbon in the fuel itself. Yet, concerns remain regarding toxicity, engine adaptation, and production methods. Methanol may offer transitional advantages because existing infrastructure can adapt more easily in some regions. Nuclear propulsion occasionally enters discussions too, especially because nuclear-powered naval vessels already operate successfully. Yet applying nuclear systems broadly to commercial shipping introduces political, regulatory, economic, and security complications far beyond engineering alone. Some experts believe future shipping may ultimately rely on multiple fuel systems evolving simultaneously, depending on route type, cargo requirements, and regional infrastructure. Others suspect entirely new propulsion concepts may still emerge unexpectedly as energy technology changes. What makes the future especially fascinating is that some solutions involve reviving ideas from the distant past in highly modernized forms. Wind assistance, once humanity's primary method of ocean travel, is quietly returning to commercial shipping through advanced engineering. Experimental vessels now test enormous automated sails, rigid wing systems, and rotating rotor sails capable of harnessing wind energy to reduce fuel consumption. These systems do not replace engines entirely, but they may supplement propulsion significantly under certain conditions. The irony feels almost poetic. After centuries spent replacing wind with industrial power, the shipping industry may partially circle back toward aerodynamic assistance because fuel economics and environmental pressures increasingly demand efficiency from every possible source. Hull design itself continues evolving too. Future container ships may look subtly different as engineers search for ways to reduce drag, improve stability, and optimize energy use further. Some researchers study air lubrication systems, where bubbles beneath the hull reduce water resistance slightly. Others explore lightweight materials, improved coatings, or advanced hydrodynamic shaping. Even small efficiency gains matter enormously at global scale because these ships travel millions of miles over their operational lifetimes. A tiny percentage improvement repeated across entire fleets can save massive amounts of fuel and emissions. Ports are changing alongside the ships. Some modern ports already resemble giant automated ecosystems more than traditional docks. AI-assisted logistics systems coordinate cranes, autonomous vehicles, storage locations, customs processing, and cargo routing continuously. Future ports may become even more digitized, integrated, and predictive. Certain analysts imagine shipping networks where vessels communicate directly with ports long before arrival, allowing unloading systems to prepare dynamically in real time. Cargo routing could eventually adapt automatically based on weather, congestion, geopolitical events, or market demand. In theory, future shipping may behave less like isolated voyages and more like one continuously synchronized planetary logistics network. But increasing automation and digital dependence also create new vulnerabilities. Cybersecurity became a growing concern across maritime industries because modern ships and ports rely heavily on interconnected software systems. A serious cyber attack targeting navigation systems, cargo management platforms, or port infrastructure could potentially disrupt trade at large scale. Some experts quietly worry digital fragility may become one of the defining risks of future shipping. Others argue decentralized AI systems and stronger cybersecurity standards will gradually improve resilience. Again, there is no universal agreement. Complexity itself may be becoming the defining feature of modern maritime systems. Climate change introduces another layer of uncertainty the industry cannot ignore. Rising sea levels may reshape coastal infrastructure over coming decades. More extreme weather patterns could affect shipping routes and port operations. Arctic sea ice decline may eventually open additional seasonal trade routes across northern regions, although the long-term practicality and environmental implications remain heavily debated. Some shipping companies already study how changing ocean conditions could alter future logistics patterns. But predicting these shifts remains difficult because climate systems interact with geopolitics, economics, infrastructure, and environmental regulation in unpredictable ways. Perhaps the most important question surrounding future container ships is not technological at all. It is philosophical. Modern civilization became deeply dependent on the assumption that goods can move continuously, cheaply, and reliably across oceans forever. Nearly every major economy now depends on global maritime trade networks functioning smoothly every day. Yet the larger and more optimized these systems become, the more interconnected and potentially fragile they may also become. Some analysts believe globalization will continue expanding through increasingly advanced shipping infrastructure. Others suspect rising geopolitical tensions, environmental costs, automation disruptions, or regional manufacturing shifts may eventually slow or reshape global trade patterns significantly. The future could involve even larger ships crossing oceans more efficiently than ever before. Or it could involve smaller regional networks balancing resilience against efficiency differently. Nobody truly knows. But perhaps that uncertainty itself makes these ships feel so strangely compelling. They are not merely cargo carriers anymore. They became physical symbols of how humanity organized the modern world, through connection, movement, energy, data, and industrial coordination operating across planetary scale. Somewhere tonight, while cities sleep and highways empty beneath the darkness, thousands of container ships continue moving slowly across the oceans, carrying pieces of modern life between continents. Most people will never see them directly, yet almost everyone depends on them in ways they rarely notice. Phones, food, clothing, medicine, machinery. Entire economies quietly travel inside steel boxes stacked above dark water beneath the stars. And maybe that is the most fascinating part of all. Humanity built floating cities powerful enough to shrink the planet itself. Yet those same ships remain permanently tied to forces older and larger than civilization. Wind, waves, currents, storms, fuel, geography, and the fragile balance between efficiency and survival. No matter how advanced future ships become, the ocean will still be waiting beyond the harbor. Silent, unpredictable, vast. And somewhere out there, under the glow of navigation lights reflecting across black water, the next generation of these floating giants is already beginning its journey into a future nobody fully understands yet. Thanks for spending this time with me tonight aboard these giant floating cities of steel. If you enjoyed the journey, don't forget to like, subscribe, and come back for more calm engineering documentaries here on Sleepy Systems.